Hi everyone. In this video, I want to discuss about the disjoint site union data structure. So before that, I will assume some familiarity with graph theory, like just the basic things, what nodes are, what edges are, directed graphs, undirected graphs, and so on. But as I said, just the basics. And then I want to basically solve the following problem. So given that I have some nodes like this and some edges like these, I might be asked whether two given nodes, so for example, whether this node and this node, lie in the same connected component or not. So, what do I mean by connected component? Well, it should pretty much make sense intuitively, right? So, this, for example, is one connected component, whereas this entire thing is another connected component. Note that this is only for undirected graphs. So, we can have some more complicated graphs like these as well. So let's say this is U and this is V. So here maybe you are asked to check whether they are in the same connected component. Now a simple algorithm, if you know DFS or BFS, it can be just start from this node U and then do a traversal of the graph. Obviously you will only visit these nodes if you start from your node U, and you just need to check whether you can visit this node V or not. However, if your graph has, let's say, V nodes and E edges, or rather I should say the set of nodes is V and set of nodes is E. So we will denote the number of nodes as N and the number of edges as M. Then it can potentially take up to order N plus M time per query. So what if they asked you a very large number of queries? So what if they ask you like K number of queries and your graph is also very large? So let's say N is around 1,000, M is around 100,000, let's say, and k is also very large of the form 10 to the power 5, so another 100,000. In that case you would be taking a lot of time to answer every query, so you will be taking n plus m time to answer every query, and there are so many of them. But I mean, the problem looks simpler, right? You shouldn't be taking so much time in every query. I mean, visually if you just see, it's very easy to answer whether they are in the same component. So why is it so hard for a program to do so? Well, one thing that you can do is, given this graph, you can already find its connected component before even processing the query. So before you get any queries, what you do is you pre-process. So in the pre-processing step, using one DFS again, you can figure out what are the different connected components, assign a label to each of the connected components. So for example, for every node in this connected component, the label is, let's say, A. For every node in this connected component, the label is, let's say, B, and so on. And now during the query, you can just check whether the labels of the two name or not. So checking whether the labels are same is basically doing two accesses into arrays. So that is just a constant time operation, right? Because you have already figured out what are the labels. Then pre-processing step takes n plus m time because you are doing a DFS or a BFS. But answering every query is effectively order 1 per query. So if you ask k queries, you can answer all the k queries in order k time. However, whenever we are talking about pre-processing, we should also note that after the pre-processing is done, it is a bit hard to change the graph, right? So what if you want to add an edge like this? Well, the pre-processing step is over, right? So even if A and B are in the same connected component now, you won't be able to tell that. So we need something which is a bit more relaxed. That is a different data structure, which is a bit more flexible with what we can do instead of just a simple DFS preprocessing. This is how, this is where disjoint sites comes in. So the basic idea of disjoint site is basically to maintain these things, these connected components. Now, instead of a connected component, we can also think of them as different sites, right? So one site with label A had everything which was connected. One site with label B had everything else which was connected. And they are not connected with each other. So the idea is you want to have a data structure in which you can store certain sets. Each set will have some nodes, and you can basically then query whether two nodes are in the same set or not. Now, I'm not saying that query will be constant time yet. We have to figure that out. Now, let me go on with what the actual data structure looks like. So, what we do is initially we have just the single nodes themselves as their own sets. Then we start processing the edges one by one. So, let me just delete this edge because it was never meant to be there. Right. Now, when we start adding the edges one by one, so for example, at first we add an edge between these two, then these two become connected. Now let's say we add an edge between these two. Now these two become connected. Now let's say we add an edge between these two. How do we represent this structure? Well, we basically make use of trees.
Now here I should mention that the edges that I am adding here are actually edges of the graph. So we are processing the edges of the graph one by one, and we are adding those same edges between those same pairs of nodes here in this symbolic graph that I have drawn.
So whenever we are adding this kind of an edge, we essentially make one the parent of the other. So we select this, and then this becomes a child. So now this is one component. Same with this node, when we add an edge, let's say we make this a child, and I will talk about the rules of which node we make a child and which node we keep a parent in a bit. And now this is a child. Now, for example, when we add an edge like this, then this entire thing, let's say we shift it down, and this is just I'm doing it symbolically. Then we add an edge like this. Let's do some examples here. So, for example, we delete this node, we actually add this edge. For these two, again, we add an edge, and then we add an edge between this guy, and this node.
Now here again I should mention that all the black lines or the black edges that I've drawn till now are edges in the actual graph. But now the edge that I'm going to draw can basically be from any node in the left tree to any node in the right tree. However, we will not directly combine the nodes, we combine the root of those component trees in this picture.
Now, how do we combine? Where do we exactly attach which child? What is going on? Well, the key thing here is we always attach one of the nodes as a children of the other node. So we will take this entire thing, move it, let's say here, and then add an edge like this. Now note that the tree is not necessarily a binary tree. It can be a NRE tree as well. But the point being that these thing is now a connected component represented by a set. This is another connected component.
Let me try to take another example here just to show you guys how the graph is exactly working. So, for example, let's say my graph is like this. So this is, let's say, E1, this is, let's say, E2, this is, let's say, E3, and this is, let's say, E4. I will talk about how to merge um, graphs with these kinds of edges in a bit. But for now, let's just assume that the graph itself was a forest, just for simplicity. Actually, let me make this E3 and let's make this E2. This is, let's say, node A, this is node B, node C, node D, node E, node F. And let's say we also have this edge. So first we have A, B, C, D, E, F. Now first we add an edge between A and B. So A becomes the child of B, let's say. Then we add an edge between C and D. So again, let's say this is what happens. Then we add an edge between these two guys. So between these nodes and these nodes. So now where will we put this edge? We will put this edge from the root of this component to the root of this component, or the other way around. So the root here is D, the root here is B. So we will join one of the roots as the child of the other. So let's say we are joining like this. Now we process F to E. So let's say we make F the parent. So kind of like this. Now this E5, E5 connects E and D, right? So D is a root, but E is not a root. So we will not be adding this edge. We will be adding an edge from the root of the component to this D, or the other way around. We add an edge from D to F. But the actual edge is between D to A in the graph. But here we actually add an edge between the roots of the trees containing the two nodes that my edge is trying to connect in my original graph. So in some sense, this edge is not exactly equivalent in this tree, but we are basically adding a corresponding edge in our tree. The diagram is a bit messy because I wanted to keep these nodes like this, but hopefully you can see that this is still a tree structure. Now we can have multiple edges, like in the sense that we can have an edge like this, which is E6. In this case, both the nodes are in the same tree. Well, think about what we will do in this case. I have explained this later on in the video as well.
Now, if we want to query if two nodes U and V are in the same connected component, the trick to checking that is whether the root of that tree is the same. So for example, if this node is U, then all you have to do is just traverse up to the root, and let's say V is this node. So we again traverse up to the root and just check whether the root is the same for both of them. If that is the case, then we are done. If that is not the case, then let's say V is here, then the roots are actually different. So they are not in the same connected component. And I will leave it to you guys to maybe draw a few more diagrams and see why this structure still preserves the connected componentness of the graph. Now, I left out one key thing. What if we are adding now an edge between two nodes in the same connected component? What if we are trying to add this edge? Now, the point being, we wanted to have a tree structure, and this additional edge does not give us any more information about the connectedness, right? We already know that all these things are connected. What does adding this edge help us with? So we just ignore this. Now, how do we actually go about implementing this structure? Well, we do not maintain adjacency lists. We just maintain the parent pointers, and that is enough. So let's get down to some coding. So I will be coding this out in C++. I've just created one additional macro for this, which is for I comma n, which just means I from 0 to n minus 1. Now let's create a class for this. So let's call this disjoint set union, or rather just let me keep it as a struct, simply for example. Now you need a parent array. So remember that when we are representing trees, we can either do so using adjacency lists, or a simpler way of doing that is just by maintaining which is the parent of every node. So let me create a parent array. Now when I create this, the constructor, I will pass in how many nodes are there in the graph, and then initialize this. Now what is the parent of the root? Sometimes we set it to -1, but here I will actually set it to itself. If something is the root of the tree representing its connected component, then the parent pointer of the root will be the root itself. So for that, I just do this.
Okay, now let's try to build our find function. So find is essentially like the find root. So given a node, we want to find the root of the node in the tree in which the node is. So for that, I guess if it is already the root node, which is denoted by node is equal to parent of node, right? Because only for the root node this condition is going to be true, then we just return the node itself. This corresponds to this case where we are actually present at the root node of the tree itself. Now if we are present at some other node, we will basically just go up. So we just do a return find of parent of node, which is basically calling find but now on the parent of v. So this is how we are actually going to move up the ancestor chain. Next, we should include a merge function which takes in two nodes a and b and is equivalent to placing an edge between the nodes a and b. Here we are essentially merging their two connected components, and we do
Root
so
of A,
by making one of the roots
which
the
is the
child of the
root
other
node
root.
of
So root A
component
is
A,
basically the root of
and
the
then
tree in which
I also
the
find
node
root
A
of
is in.
B,
The root B is
and
root
then
of the
I
node
just
in
set
which node
the
B is in.
parent of, or
And then
rather
we
the
just
root of
select
one
that,
connected component
okay,
in
for
the other.
root A, we make its parent as root B.
Now, one thing we are missing here is, what if they are already in the same connected component? Let us just create another function which is same, and it will also take in two parameters. So here I am actually calling it. If they are in the same connected component, just return. Let us now implement this function. It will return a bool, check is same, and I will just check whether they have the same root or not. That is it. So now let's quickly test it out. Let's say we have 5 nodes. Let's say we do 1 to 2. So we merge 0, comma 1. We merge, let's say 1, 2. And we also do a merge like 0, comma 2. Again, this shouldn't make any difference.
Now again realize that these 0, comma 1, 1, comma 2, 0, comma 2, these are actual edges in an actual graph. And we are basically using the endpoints of those two edges to call merge on our DSU data structure.
And then we create another connected component. Let's say 3, comma 4. And now let's check out parent of each of them. Now notice that 0, 1, 2 should have the same parent, whereas 3 and 4 should also have the same parent, but different from this cluster, right? Let's check out dsu.0. Rather, just let me write a for loop. Let me try to run this. So this is just as we expected. The first three have the same parent, meaning they are in the same connected component. And the last two have the same parent, meaning they are in the same connected component. Now, is this much better? Are we actually improving our complexity? I mean, if you think carefully, then not really. Why? So let's say we have all these nodes. And then you connect the parents like this. So this becomes a parent pointer. So you first merge these two. Then you merge this thing with this thing. So the parent pointer actually comes like this. Then you merge this thing with this thing, this entire connected component. So this is the parent pointer, and so on. So in our current strategy, we are always making the root of the second one as the root of the overall thing, right? So parent of the root of first one becomes root of second one. So the root of second one is actually the overall parent now, or rather the overall root now. So this kind of a linear structure might form. Now, I hope you see where I'm going with this. What if you called parent on this node? What if you call find parent on this node? You have to traverse the entire chain to go up to the root. Now, if there are n nodes, you are still taking order n time, which is slightly better in the sense that we were initially doing n plus m, where m is the number of edges. Now, obviously, m can go up to n squared. So m can go up to n squared. Here we are still doing only order n because we are traversing upwards in a tree. So in that sense, it is better. But I want to do much better. So I would now like to use two tricks to basically make our thing much faster. So looking from this example, right, the basic idea is we want to somehow balance things out so that we do not form this kind of a linear chain. That is the first optimization. We will try to balance things out by weight of the tree. So what do I mean? So our problem currently is, let's say we have these kinds of trees, and let's say this is another one of our tree. So these two trees represent two different connected components, right? Or rather, we can say two different disjoint sets. Now we are processing an edge which is basically, let's say, connecting these two nodes. So for that, we know that either this must become a child of this or this node must become a child of this. Now the question is, which one should we do? The trick here is very simple. Just keep track of what is the total size of this tree. So let's say that is W1. And similarly for this, that is W2. Then if W1 is less than W2, that means W2 is larger, then make this as the child and this as the parent. Or in the opposite case, if W1 is actually larger, then just do the opposite thing. Make the W2 tree as the child and the W1 tree as the parent. Now, for example, here it is 1, 2, 3, 1, 2, 3, so W1 is equal to 6. Here it is 1, 2, 3, 4, 5, 6, 7. So actually our first case was true. So this would have been the root node of the entire connected component. Now, how does this help? Well, the trick here is to see like this. All of these nodes, since they're connected, at some point they must have been merged. So when they had been merged, they would have all followed the same exact algorithm that whichever one has the higher weight, that gets to be the parent component, or rather, that root gets to be the parent. So now imagine this. Select the deepest node in the tree. Okay, so let's say there were more nodes, and this was the deepest node, the one with the maximum length. Now, the issue initially was this deepest node could have been potentially n level deep, right? In our previous example, if we carefully crafted the data like that, like the processing of the edges, if we did in a particular order, then it could have been a linear chain. In this case, however, consider when we are traveling upwards. Every time we travel upwards to a new parent, then at some point there must have been this component, and there must have been this other component, and they would have been merged, and this node was the root node for that. That means this one was W1 and this one was W2. Now, when we are here, the number of nodes in the subtree is W1. When we are here, the number of nodes in the subtree is actually W1 plus W2. But W2 is greater than W1, right? That is why this got to be the parent. That means this is at least 2 times W1. Now, why the equality sign? Well, it could be that they have the same weights, in which case we just assign either one as the parent. But in any case, W2 is not smaller, right? So this inequality holds. Now see this. The subtree size was W1. The moment we jumped the edge to the parent, the subtree size here is now twice W1. Now again go to the parent. Then if this subtree size we call it, let's say X, then this subtree size would be 2x by the same logic. But X is already 2 times W1. So this is actually 4 times W1. Now again when we climb a parent, this subtree size again doubles. So we have a repeated doubling. Now initially we are at this node, the subtree size is just 1. The moment we climb a parent, the subtree size becomes into 2. Now when I say into 2, I mean it must at least be into 2. Again when I climb a parent, it must at least be again multiplied by 2. It can be greater, but it must be at least this much because of this thing, and so on. But again, we have only n nodes, right? So if I multiply 2k times, this just becomes 2 to the power k. In the best case scenario, like this is the minimum number of nodes after k jumps to the parent. Now this must always be this. From here, it should be easy to derive that k should always be less than equal to log n base 2. Now remember that k is the number of times we are jumping parents. So that is exactly the depth of this maximum deepest node. So the depth now becomes from order n to order log n, which is a great improvement, right? So now when I'm checking for is same, when I'm checking for the parent, or rather the root of the tree, I just have to climb log n parents and then I'm done. So the find operation, which is at the heart of our structure, just takes log n time. So if we again check our code, is same then also takes log n time. Merge operation then also takes log n time. And find, we just proved that it takes log n time. So how do we implement this extra weight structure? So we just create another weight array. and then set the weight of I to be equal to 1. Now here we check, or rather let's just say we create two weights. Weight W1 is the same as weight root A, and W2 is weight of root B. Now if W1 greater than W2, then root A is the heavier thing. So we should make root A as the overall root. So parent of root B is now actually root A. Otherwise, and this includes the equality case as well, we choose the other way around. So we make root A as the child and root B as the parent. Now note that we still need to update the weight of the root. And you should also notice here that we are only ever going to check for the weight of the root. We never need to check for the weight of any other node in the tree. So in any case, I should update the weight of root A, which is now the overall root, to be W1 plus W2, and weight of root B is also here to W1 plus W2. Right, so this root A is the same as this root A, and this root B is the same as this root B. And this is the only modification needed.
Sometimes it is called balance by weight, sometimes it is called small to large merging. Well, the latter is kind of because you are merging the smaller component into the larger component. But the key idea is this repeated doubling, where every time you go up the chain, you double your subtree size. And since you can only double at most log n base 2 number of times, your entire thing is bounded by log n. Like the number of times you can jump up is bounded by log n. That binds our find function to log n complexity. And so since the other functions are just dependent on find, we just do a log n operation cost for every function. Now, the second trick is to make it even faster. Let me draw this tree. This is a probable tentative structure, right? Now, let's say we are calling u comma v, u comma w, u comma z, where u is, let's say, this node. Now, all of them have this u component as the same, but every time we call find, we have to jump up like this, right? Now, notice that we do not have any requirements for the tree to be binary. In fact, we do not care at all. We are not storing left and right children. We are storing the parent pointers. So for all we care about, this node might very well have had a link to its parent. That does not break any of our assumptions, right? If this just has a link to its parent, we are still done. I mean, sure, some of the constraints that, oh, this node, like when you are jumping, then this node must have at least twice the number of nodes in your subtree, that might be broken. But realize that in any case, the maximum depth here is log n. And when you are going to merge this component to something else, this weight is still being maintained under this root. You will never be merging something like this, right? You will always be merging it to the root, and for that the root still has the weight of this node accounted for, this u node accounted for. So if I just link u to its root, I would still be okay. But doing this separately for the nodes is a bit haphazard. It might take some additional complexity. So what the solution here is, every time we traverse such a path like this, we set all of these pointers to the root. So all of these parent pointers get set to the root directly now. So after I do a find u, where u is this node, my tree structure essentially becomes something like this. Now, any additional further searches on u, anything in this path also get reset to u, as in their parent just becomes u. So all of them also can now reach the root in constant time. This is very neat, right? We just query this node and all the nodes in the path from u to the root, all of them gets their parent pointers set to root. Now, this might seem a bit heuristical, and the complexity analysis is not that easy. Maybe I will make another video about it. But overall, what happens is your complexity goes from log n to something called alpha n, where alpha is called the inverse Ackermann function. Point being that for any value of n, so when I say any, I do not mean infinity, I just mean that for any practical values of n, alpha n is less than 5, which is very near constant time, but then again, it is not a constant time thing. This alpha n does maybe grow out to infinity if n is infinity, but point being, for all reasonable values of n, this is true. Now you might ask, well, what if we have this kind of a tree structure somehow, and then we are calling find u here? Will it always be alpha n? I mean, technically no. This alpha n complexity is actually amortized. This is actually an amortized time complexity. So for every operation, it might not be alpha n, but for the first k operation, you only have to pay a total of k alpha n. So it kind of averages out. So again, how do we actually implement this in our code? Well, we just make a slight change in the find function now. Now we do if, or rather, let's just keep this part. Or actually, no. Now we just do if node not equal to parent of node. That means it is not the root. Then I set parent of this node to be the root that we find, which is find parent of node. So this is actually just going up above, right? One step up. But the root that I find from here, I'm setting it to be my parent. The node I'm at, I'm setting it to be my parent. And then I just return parent of node. Now this technique is called path compression. Since we are basically compressing this path and setting all the parent pointers for all of these nodes to be the root node. Now this is also called rank compression in a lot of cases. Not exactly this. What I have implemented is merging by weight, but rank compression is also a similar concept where instead of merging by weight, we check whichever has the greatest depth node and then merge accordingly. But the basic concept is the same. If you combine both of them, then we get this inverse Ackermann function, and this is really good. Now the question is, why did we go to all this trouble? We already had a way of answering everything in constant time. Well, now notice this. Even in your graph, if you now want to insert a new edge, we still have to pay a very little cost and still maintain all the information. But in our previous case, we would have to do the DFS all over again. So here we are only paying order alpha n cost, whereas in the previous case, we would have had to do the DFS all over again. Deleting an edge is actually harder though, but insertion of edges now becomes very easy. So this is what the disjoint site union problem is all about. This is the data structure that we use, and this is a sample coding of it. Hope you enjoyed the content. Thanks for watching. See you soon.